Hello everyone, my name is Thanasit Bonam from Microsystem Research Group, Newcastle University. I would like to present a brief of my thesis, memristor-based design solutions for mitigating parametric variations in IoT applications. Let's start with the motivation. Recently, the number of IoT devices is growing rapidly. This is due to the wide range of applications, for example, agriculture, healthcare, and disaster warning. And the demand of advanced features such as machine learning is also increasing, and these features are power hungry and result in the lower reliability. In case the devices are powered by the energy harvester and more maintenance required in case the devices are powered by batteries. And technology scaling is a solution to this problem because the smaller transistor can consume less power, and this provides better reliability and less maintenance requirements. And we can integrate more advanced features into the smaller dies. However, the technology scaling has an impact of parametric variations. For example, the process, voltage, and temperature variations, as well as aging. And the variations results in the timing variation, where the clock signal may arrive the register too early or too late. We can use the delay element to mitigate this problem. However, it causes a higher number of switching devices and a higher number of data storage required, which result in the higher power consumption. And this becomes our first challenge to design memristor-based delay elements to save the power by reducing the switching device and to use the memristor as an on-site data storage. We found that the memristor's value is also highly temperature sensitive. Therefore, we need a temperature model to enable the temperature compensation and temperature sensing applications. And to read the data inside the memristor, we need a memristor decoder. And to achieve a high resolution data, we need to spend more energy for the decoding process. And this is a problem for IoT devices because the harvested energy is uncertain. Therefore, we need a scalable resolution based on the energy budget. And this becomes our second challenge to design a solution scalable memristor decoder with temperature awareness. To summarize our contribution to address the first challenge, we propose methods for utilizing memristor to improve the energy efficiency of delay matching in CMOS circuits. We focus on two-phase asynchronous bundle data circuit because it provides a better performance, higher power efficiency, and smaller area. To work with this kind of circuit, our delay element should have a symmetric propagation delay for both rising and falling transitions. And we design memristor-based delay element, MEMDE, which is our first version. We also designed a second version with an intent tuning free, and it also provides a symmetric propagation delay. We realized the excitation time model to estimate the tuning power width that associate to the memory stand chip. To address the second challenge, we propose methods for improving the temperature awareness and energy robustness of the memory stand decoder. So we realized the memory stand versus temperature models for titanium dioxide and silver chalcogenide memory stars. And we design and demonstrate a resolution scalable decoder with temperature compensation. So let's see about our MEMDE. The application of our MEMDE can be both synchronous and asynchronous circuit. For synchronous circuit, we can use our MEMDE to adjust the clock timing to cover the propagation delay of the data path. And for asynchronous circuit, we can do the similar thing. We can use our MEMDE to adjust the delay of the request signal to cover the propagation delay of the data path. And to do this, we also need some extra components like error detection register to be able to detect the timing variation and send the error signal to the controller. And the controller can adjust or increase the delay of the delay element. We may include a counter in the controller to be able to decrease the delay in case the timing variation does not exist for an amount of time. And this error detection register and controller is beyond of our scope. This is our MEMDE design. The top one is our first version. It can provide a delay. It can vary the delay, but it has an unintended tuning and unbalanced slicing and falling delay. So we designed our second version, which is unintended tuning free, this circuit, and provide nearly equal rising and falling delays. In this circuit, the delay can be vary from 550 picosecond to 1.44 nanosecond, with 13 times less power than the max DE. We then simplify the memory transistor circuit to be in form of a voltage divider to estimate the tuning power width and the memory state shift, and we obtain the 7% maximum error. For the temperature model, we use Arrhenius relation to estimate the temperature effect on the off memory stands. And we use the data from the literature to calculate the model parameter for the titanium dioxide memory star. We achieved the R square of 96%. And we also run the temperature experiment on the silver chalcogenide memory star chip. And our extracted model parameter achieved a square of higher than 88%. For the memory stand decoder, it is an essential building block in memory chip application, for example, multi-bit memory and dot product engine, which is massively used in machine learning application. The decoder receives the input current, which correlate to the memory stands, and it provides the output. It provides the multi-bit digital output. This is our memory stand decoder design. We design and demonstrate a 2-bit decoder, and here is the list of its features. It has a resolution scalable by configuring the reference sources in the DCCS. And we also demonstrate the temperature compensation using the proposed model. And this decoder also provides a memory state interface, and it also contains a offset calibration using capacitor arrays. And this design is metastability free and resistor free, which is less sensitive to because the resistor is highly sensitive to temperature. And the performance of our decoder, the energy per comparison is 49 femtojoule, and the maximum frequency is 2.91 nanosecond, the maximum frequency of 343 megahertz. For the future work, regarding the memory state delay element, we still need to design the controller and the error detection register to complete the whole circuit, the whole system. And we also need a synthesis tool to be able to synthesize the circuit from the RTL level, which is beneficial in case we need a benchmark circuit. And we need to implement the delay element with the smaller technologies. And to do this, we need to study the relationship between the supply voltage, threshold, and memory stand. This is to determine the maximum memory stand for the target technology. And we need to study the excitation time model for the smaller technology to have a more accurate model. And for the temperature model, we need to realize the temperature effect above 378 Kelvin, including the temperature effect on the memory stand. And we need to investigate the unstable memory stand above 78 Kelvin. For the memory stand decoder, we can extend our design to implement the multi-bit memory by adding memory stand programming circuitry. And we need to improve the noise reduction for the current mode comparator. And we need to study the better temperature compensation technique. And we can also develop a memory chip temperature sensor. And thank you for your attention.